What happened in the earliest moments of the universe? What is the universe expanding into? And how do astronomers think about events happening in the past? All this and more in this week's Overtime Question Show. Hey everyone! So we're still on our live stream hiatus, and so we're going to bring you another episode of Questions from Overtime. These are the questions that got asked after we stopped recording and just continued on with the live stream. A bunch of different questions, a lot of astronomy-related questions. I think you'll really enjoy them. So enjoy this next episode of the Overtime Question Show. These came from late October. Anmol Goyal, can you explain to me what happened in the early stage of the universe and why we can't see until the actual size of the universe? I mean, there's so many things that happened at the beginning of the universe. If you go like right back, like the best way to think about what happened in the early universe is just run the existing universe backwards. Like right now we look out in space and we see galaxies that are moving away from us. And so if you were to turn this backwards, then you would see galaxies coming towards us. And eventually the galaxies would all be in the same-ish location. And so this time was when the entire universe was so kind of hot and dense that you didn't have stars and galaxies. You just had the whole universe was like the surface of a red giant star. So just imagine everywhere you looked, it was just this red glow because everything was about 3000 Kelvin. And then if you go earlier and earlier back into the universe, like that's about 380,000 years after the Big Bang. But if you keep going just a few minutes after the Big Bang, then everything in the entire universe was as hot and dense as the core of the sun. And so for about 20 minutes, you had nuclear fusion happening and hydrogen was being turned into helium for like I said, for about 20 minutes. The ratio that we have today of 75% hydrogen to 25% helium, that was all formed when the universe was like the core of a star. And then earlier than that, and fundamental forces in the universe, like the strong and weak nuclear force merged into one type of force and then merged with electromagnetism, and you can keep going back. There's a lot of books. Was it the first 6 minutes, I think, is the book? Anyway, there's a lot of really good books that tell you sort of what happened. Why can't we actually see the actual size of the universe? Because we can't see before the beginning of the universe. And the beginning of the universe is that, light has taken 13.8 billion years to reach us. That is the farthest that we can see, is the longest that light has been able to travel to us. In the future, we will be able to see more of the universe because more light will have arrived at us, but we can't see before the beginning of time. Ba Ali. I'd like to know what the universe is expanding into, if that makes any sense. Yeah, we get that question a lot. And so the universe isn't expanding into anything. So like there's two possibilities, right? One possibility is that the universe is infinite. And so like that question doesn't even make sense, right? Like what is the infinite universe expanding into? Well, it's infinite. And so you can't say, oh, well, it's expanding into something. The other possibility is that the universe is finite. And if the universe is finite, it wraps. And so you can kind of imagine that if you go in one direction, another direction, right, you're going to wrap back to your original location. And so there's no outside of everything. People sort of imagine in their mind this sphere that is expanding and maybe it's expanding into some kind of other stuff, but that's not right. Licky poo. Science communicators often talk about how looking further into space is looking back in time, but isn't that directly contradicting the theory of relativity? What we see now is what is happening now. Yes, sort of. So because of relativity, when events happen at different times depending on the observer. It's like the classic example of this is like when I say this star just exploded. And then I get someone saying, well, actually, that star exploded 10,000 years ago, and we're just seeing the light from it now. And I'm like, okay, smart guy. When did it explode for the person who's close to the supermassive black hole and is experiencing enormous amounts of time dilation? When did it explode for the cosmic ray that's moving at 99.999% the speed of light and is experiencing enormous amounts of time dilation? in the other way? When did it happen to the people who were on the far side of the universe, who could have experienced up to 30,000 years of time dilation compared to us on this side of the Milky Way? When you are aware of an event happening depends on the amount of gravity that you're in and the speed that you're going. And so you can't say that a thing happened this many years ago, because it all depends on your observer. Everything's relative. And so you can only say that it happened, you were only made aware of it now. And so then you can say that the supernova exploded because you are like, obviously it happened in the past, but you had no information about that until you see it. And so there's this idea of like the speed of causality, that events can only move through the universe at the speed of light. And when you experience that event happening depends on your local frame of reference. And so it does not make sense to say that this thing happened 10,000 years ago. It makes more sense to say, like, it is more logically correct to say that this thing happened now, even though you're seeing it after it happened, than to say that it happened 10,000 years ago. Because when you say it happened 10,000 years ago, then you have to say compared to what? Compared to who? Compared to where? Compared to when? Compared to what speed? Compared to what gravity well, right? Like it just goes on forever. But it drives people crazy when you say that. And so, like, I don't say it very much because I'm sick of people will actuallying me. Oh my God, is this what it's like to be around me? I have to ask my wife. Yeah. And so you just kind of go, okay, the light has been, the look back, you talk about the look back time, but that's actually inaccurate. That the most accurate way is to talk about the speed of causality, speed of communication in the universe. So anyway, it's, I find that funny. And that people ask me, like, what's the misnomer that most exasperates you? And it's that, right? Because I'm trying to be more accurate and somebody is actuallying me and they're wrong. And now I have to have an argument about that. But what can you do? So you're right, Licky. You're exactly right. But you can never tell anybody because it's not worth the fight. Bravo 01, Elon mentioned placing a telescope within Starship with a bigger mirror than that of Hubble. Thoughts? Yeah, it's theoretically possible. Starship has a 9-meter fairing. You could jam an 8-meter telescope inside Starship with like additional hardware outside of it. So you could fit like a mirror the size of James Webb, but just in one optically ground perfect mirror. And like when you think about the Mirror Lab, where they build those mirrors for the Large Magellan Telescope or the Gemini North and South, they're all 8.4 meters. Like that's the perfect size. Like they know how to make mirrors. So you have the Mirror Lab build you a mirror, and then you could put that on a space telescope and put it inside Starship and fly it. Starship will launch 100 tons to orbit. So you could build a space telescope that would be fat and heavy, and you could do it. So like, what am I like? Put up or shut up, Elon. Like, can people fly today on, when will we be able to do it? That sounds great. Make it happen. How's that coming? Cosmic web. What energy caused the Big Bang, and what role did dark energy play in the very beginning? We don't know what set the events of the Big Bang in motion. What was the source of the energy that set all this in place? We're here, so we know that it happened, but really our math can only go back to the point where the weak nuclear force, the strong nuclear force, and the electromagnetic force were all one force. We don't know what happened before then. And this is like we don't know how gravity tied into those forces. And we don't know what was the source of like all that in the first place. So unfortunately right now, and we may never know, and that's okay, right? Like sometimes there's just stuff that we don't know the answer to, and we just have to say, I don't know. This guy, is a black hole star or quasi-star considered a likely possibility in astronomy or just an interesting theory? I mean, the whole way that astronomy and science works in general is you come up with an interesting theory and then you try to accumulate evidence for what that thing is. And so, for example, the theory says that when a star with many times the mass of the sun dies and is no longer putting an outward force from the fusion, then the outer layers collapse inward and you get this supernova and a black hole forms, or a neutron star. And we see neutron stars out there in space. Like, we can detect them, they're rotating. Think about pulsars, magnetars. Like, we know neutron stars are forming. And yet neutron stars only go up to a certain size, certain mass, and then there's nothing beyond that certain point. So like, either the stars that are more massive, when they die, they're just blowing themselves apart, or they're turning into black holes. But astronomers wanted to know that these black holes were out there. And so they gathered evidence. And so the first black hole that astronomers found was called Cygnus X1. And this was a black hole that was in orbit around another star. And the black hole was siphoning material off of its partner star and throwing radiation into space that astronomers were able to detect in a very specific wavelength, in X-rays, which matched what you would expect to see if a black hole was feeding on a star. But that's not enough. Astronomers kept going. The theory was that there were supermassive black holes at the heart of the Milky Way, and astronomers were able to use infrared telescopes to be able to see stars that were moving around the heart of the Milky Way, like comets going around the sun, and they were able to measure the mass of this invisible spot. Like, there was nothing there, and they were able to measure the mass at 4.1 million times the mass of the sun. And so that was more evidence that black holes are real. And then the Event Horizon Telescope was able to actually image the event horizon of the black hole at the heart of M87, as well as the black hole at the center of the Milky Way galaxy, with incredible resolution. And you could actually see the shape of the event horizon and match that against the theories predicted for what a black hole event horizon should look like. Think about Interstellar, and you got this match. And so just the evidence continues to build. Like, could they be wrong? Sure, they could be wrong. But every time more evidence is gathered, the more we know that these things are real. Like, I don't think there's very many people out now who would say, oh no, black holes aren't real. And you'd be like, well, how do you explain these X-ray stars? How do you explain the stars moving in the middle of the Milky Way? How do you explain the pictures taken by the Event Horizon Telescope? How do you explain, like, it goes on and on and on. Brian Walker, will the ELT do much infrared observing? So the ELT, that's the European Extremely Large Telescope, this 39-meter telescope that is under development by the European Southern Observatory. And it's going to be operating out of Chile later on this decade, and it will be the largest telescope ever built. And sort of the prototype for the Extremely Large Telescope is the Very Large Telescope. And these are the collection of 8-meter telescopes also in Chile. And they are a near infrared telescopes as well as optical telescopes. So they can both observe in the near infrared and in the optical region. So yes, the Extremely Large Telescope will also be able to do that near infrared astronomy in addition to visible light astronomy. I'm not sure like what the breakdown is going to be. I mean, different kinds of targets require different wavelengths. And so I'm not sure like how much it's going to be doing, but it definitely will be one of the primary ways that it's observing the sky. Infrared is really good for finding, say, exoplanets around newly forming stars. A lot of the observations, the direct observations of exoplanets that have been done in infrared. And so, like, some of the most exciting images that we're going to try to see will be planets around stars, and that's going to take infrared. YouTube Joseph WM, what would happen if a starquake hit Earth? Would it cause a mass extinction? And if so, what would be the subsequent disasters and effects, and what things would it create? So a starquake is when a neutron star crust crunches down. And like, you would think like, okay, a neutron star, it is this ball of neutrons that is reached its final size, but that's actually not true. Neutron stars have layers. And so maybe they're going to have these neutrons at the core layer, but maybe they're going to have some kind of fluid around that made of neutrons. And then maybe they're going to have like regular particles around that, some kind of like atmosphere, but mashed down. And neutron stars are cooling as they age. And as they cool, they shrink. And so you can get almost like plate tectonics. Like as the neutron star shrinks, you're going to get things kind of crunching down inside of it. And you get this release of radio waves, like an enormous amount of energy is released off the surface of the neutron star. It interacts with the magnetic field, and you get this release of radio waves that tells you that the starquake happened. And like the best tool that we have to be able to observe this, there is the NIAC instrument that's on board the International Space Station. It has been able to observe starquakes happening on neutron stars. I can't imagine a starquake having any impact on Earth. Like sure, if we were in orbit around a neutron star when this happened, then that would be a problem. But neutron stars are hundreds of light years away from us, and so I wouldn't worry about it. If we were in orbit around it, then it would be a blast of high energy radiation that would strip away the ozone layer. And so you have increased amounts of radiation that are able to reach the surface and theoretically can cause a mass extinction event. Uncle Eric, do you think that Io has tectonic plates? I don't think so. Io is more like hotspots. Like we have hotspots on Earth, like the Hawaiian Islands, where you've got this gap in the crust where magma is coming up and you've got volcanic activity on the surface of Io. And it's thought that that's what you have on Venus. Like Venus never had tectonic plates. Instead, it had occasional hotspots. And so you would have volcanic activity on the surface of Venus. And then every now and then, maybe Venus turns itself inside out, and like maybe that would happen on Io as well, but I'm not aware of any evidence that says that Io has tectonic plates. J.R. Corday, your NIAC coverage this year was some of those fascinating interviews you've done. When will the 2024 NIAC grants be decided? Do you know of any interesting projects vying for next year's grants? The NIAC grants they usually come out in the beginning of the year, so February, I think, but there's like a conference that happens in November, and they have a teleconference, and so I sign up for the teleconference and listen to all the presentations, and then I worm my way into the hearts of all of the people who are going to be giving presentations, and then I try to do interviews with them. It's such fertile ground. Like you, I'm so fascinated to talk to these people about the research that they're working on, the technology that they're proposing. Every one of the ideas is just like so out of the box. And for me, like that's what NASA should be, is more of that, right? Less space stations and more fusion drives. But I understand that, you know, there's constraints and deliverables and so on. But yeah, it's always baffled me that other people don't report on it in the same way. And this year was the first time that we tried to get them all. Like if you look back, I've even interviewed the director of NIAC. And so each year I try to sort of every year I should have the NIAC director talk, and then we'll do the series of interviews. But maybe that'll get more pressure, because I only get about half of them responding to me, and I need them all. Like I want to collect them all. And so they need to understand that if they talk to me, then this will be valuable for them, and we will be able to help them promote their stuff. David Baker, have any of the models been produced that explain the pairing of these jumbos that have been discovered? So the jumbos, these are the Jupiter, I forget the acronym, but it's like the Jupiter rogue planets that were found in the Orion Nebula. And 9% of those rogue planets were in binary configurations. So you've got two Jupiters orbiting around each other. What's the model? I mean, like to find one, okay, great. It was kicked out of a planetary system and now is floating free. It was kicked out of the house. But to find two in orbit with each other, then they probably either through some weird three-body interaction that got them into orbit around each other, or they formed together from their own little mini protoplanetary nebula and just went straight into gas giant, super Jupiter form. So it's so exciting. Like finding these objects in the Orion Nebula is one of the most exciting discoveries of the year. And astronomers are going to be digesting this for decades. Like I wouldn't be surprised if somebody comes up with a new type of telescope that's able to detect the presence of rogue planets, Jupiter mass objects out across the universe. Like, we're starting to get this sense, this whole new paradigm that there is another class of objects out there, these rogue planets, and they're incredibly common. They're everywhere. And knowing where they are and how they formed and where their movements are and how they get kicked out of solar systems. Like, there's so much meat to be digested there that I think we're going to see a lot of exciting work. So just like don't panic. We're right at the very beginning of this. Bill Seidel, probably a dumb question, but here it is. If we can detect or see the CMB, and the CMB is the farthest object that we can see, how is it that we cannot see the galaxies that are out of our visible horizon? The CMB is the earliest thing that we can see. You know, the light has been traveling for 13.8 billion years to reach us, and there was nothing before that to reach us. So, like, if the universe goes on forever and you could instantaneously just move yourself 1 billion light years in any direction, you would see galaxies close to you, galaxies redshifted away from you, quasars at the farthest reaches, and then you would see the CMB. And if you moved 50 billion light years in one direction, like well beyond what is our observable universe, you would see galaxies close to you, galaxies redshifting away from you, quasars at the very limits of what you can see, and then the CMB. Like, you will always see the same thing, but just different galaxies, you know, different players in the playing different roles. But at the end, you just see the same thing, because it's about the amount of time that light has taken to reach us. Eerie. Could you ride a black hole's polar jets? Yeah, in theory, sure. You know, there have been proposals for having futuristic ways of using the solar wind coming off of the sun as a propulsion system, as well as like using an electric sail that will interact with the magnetic field of the charged particles that are coming off of the sun. And the sun is like nothing compared to a black hole's polar jets. I mean, they are going at, like, while the sun's solar wind is going at hundreds of kilometers per second, these polar jets coming off black holes are going close to the speed of light. And so they would be probably the best, like the most efficient, like most powerful propulsion system you can possibly imagine out there in the universe. They're just waiting for us to get to them. All you have to do is get to a quasar that is sending out polar jets, which, you know, could be a challenge. Now, I'm going to continue on with the book club, what I am doing for my summer reading. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Bill, David Gilton, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mazzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Last week, I said what I thought was the best science fiction book, which is Fire Upon the Deep. And so I wanted to continue this journey with Vernor Vinge's work, and I read Rainbow's End, which is a book that had been on my shelf for a while, and I'd never gotten around to it. And the story is of a man who was suffering from Alzheimer's, who a cure is invented, and he sort of wakes up from being in this hazy state for a long time and realizes that the world is vastly different from the one that he got sick into. And that is just like one part of the story. And then there's like potentially artificial intelligence and people grappling with new technology as it's approaching the singularity. And it wasn't as good as Fire Upon the Deep, but it is a really interesting book. And when you think about when it was written in 2006. So it is almost 20 years old and was written just before the smartphone revolution. And so a lot of the technology that Vernor Vinge predicts, some of it is just eerily correct, and others is a little off, and we're not quite there yet. But still, I thought it was a fantastic book, and I highly recommend if you want to continue reading. If you enjoyed Fire Upon the Deep, look into some of his other writing. This week, I'm going to be reading Aurora by Kim Stanley Robinson, which a lot of people have been recommending to me. So I'll let you know how that went next week.